So in the last lecture, I explained shift-reduce algorithm, a kind of shift-reduce algorithm. But this lecture is about a different paradigm. It's just about sequence to sequence, but also it considers the prediction of the types. And also it is in the context of lambda calculus, so a different thing, a different formalism. So there are two main approaches to semantic parsing. We treat semantic parsing as a machine translation problem, where the logical form is linearized, then predicted as an unstructured sequence of tokens. So this approach has the advantage of predicting the logical form directly from the question without latent variable. Because, last lecture, we had some problems with latent variables and those expectation maximization, those things. Here is much, much simpler, easier to learn, and less challenging things, but it has its own challenges. So early work on semantic parsing used lexicalized grammar, formalisms such as CCG. You can watch my playlist about CCG, this combinatory categorical grammar. So these formalisms have the advantages of only generating well-typed logical forms, but the disadvantage of introducing latent syntactic variables that make learning difficult. So these are great scholars, great article. Please read this article before going to the next slide, because we need these combinatory categorical semantic parsing. You need to know what is compact lexicon, but here I quickly review everything. For example, what is higher order logic? Arguments can also be functions. They're just like JavaScript, because I used to be a JavaScript programmer. I used to be a functional programmer, either in Java, Python, any other language. So these are coming from not only from programming languages like Lisp, Python, Java, and any functional programming, JavaScript, but also it is coming from the computer science. So that's why they are very important. So we have lambda calculus. You need to know what is a logical constant, what is a variable, and what is lambda term. So this is a lambda calculus expression. So this is, for example, when we say city of Austin, this is the literals. We have some predicates located in. For example, we say Austin is located in Texas. So if it is true, so the output is true. It's a Boolean expression. So you give something, some entity as an input, and it gives you a Boolean expression. So it has some type, and you can also think about it like this if you like, or if you think about like Lisp expression, symbolic expression. There are many ways to think about these things, because you need this to have a great motivation to follow. So sometimes you need to have typed lambda calculus, because to predict, to anticipate some errors that could occur. But if you use typed language, then everything becomes simple. So you understand that this is logical, but for example, this one and this one is not logical, because we are looking at it as a typed languages. So what is CCG? As I said, I have a playlist on CCG. So it's an established linguistic formalism. Great people like Steedman in 2000 and 1996 as well explains a wide range of linguistic phenomena. So it jointly models syntax and semantics. Because if you use only work about syntax, like syntactic parsing, dependency parsing, you cannot work on semantic parsing problems. So that's why we need these formalisms such as lambda calculus and these things. So CCG categories You can use it for example, primitive syntactic symbols, and noun phrase, adjective, and so on. So what is CCG? As I said, is combinatory categorical grammar. I have a playlist on this. An example could be like this. For example, if we want to say CCG is fun. So it has, not only it has a syntax, but it also has some logical forms. For example, you can say this is the syntax of that, and this is the logical form of is, but together we call it a CCG category. Let's say super tag. In some articles they call it super tag, because it's a mixture of syntax and also logical form. So not only you should predict the syntax, but also the logical form. That's why it's very challenging. But it's very interesting because once you know this syntax, it says what is this? What is S and P and then S/ adjective? So when it says NPS/ something, it means it needs that something. For example, here is adjective on the right of that. When you see backslash, it means it needs these things on the left of that. So this is important if you understand. So even this thing, this tells us that how you can arrange these things, these different combinations. And this is an example from robotics, which is really nice. For each chair could be anything. All of these are chair. So we can have, so it defines, this chair defines the set of objects for which the type of E and T, the entity and the return, which is true or false. For example, T is Boolean, is true or false. Typed constant chair returns true. For example, is it this kind of chair or is it this kind of chair? But all of them are chairs. Or another thing is definite article. We put it this type. It has the. This is the definite article. The chair. So also different examples that I've explained some of them in a different playlist. So another example is that move forward to the chair. So not only you should move in very generally moving, but also you should do it forward and also to the chair. So and operation for all of that. And then so the first two are correct. But so it predicts, so it learns these things. So the algorithm should learn that this is for chair. This is another probability. There is a probability, but there shouldn't be any probability for, so it shouldn't assign this to chair. So just the first two are correct. Or match words or phrases with their categories. As I said, S/ means you need something, that adjective, on the right of that. And backslash, it means you need something, this one, on the left of that. And so this is the logical form. This is the syntax. Together, as I said, we call it CCG category, or some people say super tag. And here you match words with their, this is a good example. You can follow if you have time. You can read this, very interesting. And it's because you understand how these logical forms are combined together to have different, to cover different spans. And so here, for example, you start from, for example, twice could have some logical form, but they, for example, this one and this one, you can combine them because it needs NP on the right of that, and the right of that is NP, so they can merge to each other. So these S/ and backslash tells us everything. They are very important because they tell us how we should combine them or not combine them or not allowed. Everything is just, so that's why this is CCG is really interesting. This CCG is invented by great people in Edinburgh in Scotland. So I have a playlist for CCG, a different playlist. I have a different playlist for context-free grammar. So you need these things to appreciate that what we are doing. So I have created different playlists and describe each of them. So you see the combination operations of context-free grammars, we have different combinations, but in CCG we have very few combinations, very few combination operations. But the syntactic symbols in CFG is few, but the syntactic symbol in CCG it's handful but can combine. And CFG uses part of speech tags, and but CCG uses categories. So this is a nice nice article that I want to explain it. So we treat semantic parsing as a machine translation problem, as I said. So our tight constrained neural net semantic parser inherits the advantages of both. It only generates well-typed logical form and has no syntactic-related variable. So, and this is a good data set, Wikitable questions. For example, Greece held its last Summer Olympics in which year? You have a table, and then you understand it's 2004 for Greece. Or other questions. So this Wikitable question data set, if you have a look at this, it's really interesting. And so this is the main architecture that we use. I think this is the work of Percy Leong that I put here, because yes, it is his work, and the reason I like these because it shows the architecture very clearly. So always we have parsing, always we have conversion, always we have a kind of ranking. And we have finally, we should execute. We should execute this in order to backpropagate the loss. So there are two key technical innovations. The first one is a grammar for a decoder that only generates well-typed logical forms, and an entity embedding a linking module that identifies entity mentions while generalizing across tables. So there are limitations of using recurrent neural network to predict tokens of logical forms, because they're compositionally they're not good, and so the lambda DCS operation is a better, simpler formalism in comparison to lambda calculus. So the idea is this: you have sequence to sequence, but also you're also learning to predict the grammar rules, and this helps having a better accuracy. And also we do entity linking before giving it to the LSTM. First we should do entity linking. So you can also augment it with different things. So the model predicts the answer to the question by semantically parsing it to a logical form, then executing it against the table. And so the decoder, an example of this decoder, for example, which athlete was from South Korea after the year 2010. So it produces this logical form, and we can go through that. First, we should review Article 2015 of Percy Leong. I skipped that. Entity linking, and then the encoder, what is the probability of each. We skip this because I have explained them in a different lecture, so I should skip this. So let's get back to the article that I'm explaining. So we want to parse this logical form, But we are also taking advantage of the types because we want to remove the incorrect parsing as much as possible to help having better accuracy, outperforming state of the art and these things that people write. So what can we do? What is this example is about? So we reverse name starting from here, from left to right, reverse name. And then reverse name, then we have this type. It needs this type. And then it needs another type. And then we move to the rest of these logical forms. We parse them sequentially, but not only that, we are predicting, because at each time step we are also saying what is the probability of each type. So this is an overview of the semantic parsing of this beautiful article. The encoder performs entity embedding and linking before encoding the question with a bidirectional LSTM. The decoder predicts a sequence of grammar rules that generate a well-typed logical form. I really appreciate this article. Very interesting. And so the training data has n question answer table triples. You have question, answer, and each table, TI, you have table, and answer, AI, to generate a set of logical form. So dynamic programming on denotations is an automatic procedure for enumerating logical forms that execute to produce a particular value. It leverages the observation that there are fewer denotations than logical forms to enumerate this set relatively efficiently. However, many of these logical forms are spurious, like spurious correlations, in the sense that they do not represent the question's meaning. Therefore, the objective must marginalize over the many logical forms generated in this fashion. So we marginalize, and that's it.